All right, so last time where we left off, it was a discussion about the mole, and it was about how to use the mole in conversions. Remember that if we were talking about the mole, and I kind of framed it in the idea that students have a difficult time wrapping their heads around what a mole is. And remember, it's a number. Mole is just a word that means a particular number, just like uh, just like dozen or pair or few or case or gross or fortnight. That was one word that we didn't talk about the other day. I don't encourage anyone who's driving to do any calculations while they're driving. I think they should just focus on driving, just in case that wasn't clear. If you're not driving, then someone else is driving, then go ahead. Anyway, I digress for that public service announcement. Good. I digress for that public service announcement. Just wanted to keep everybody safe. We then talked about how we can then say, okay, well, we know how much a mole means, 6.022 times 10 to the 23rd. We talked a little bit about how vast that quantity was, because when we thought about a mole of a piece of candy, like a tiny little candy like M&Ms or Skittles, we couldn't really wrap our hands around how much that was. And so we had some guesses, but none of our guesses were anywhere close, right? And so once we figured out that a mole of Skittles would fill up essentially around 100,000 Grand Canyons, or all the oceans in the world, we got mind blown for a little while, and we said, okay, man, that really means at the end of the day, if I can have a mole of water in a plastic bottle in my hand, then that means that water molecules are really, 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 really small. So then we started doing some calculations. We said, well, let's take the number of molecules, convert it to moles. Let's take moles and convert it to the number of molecules. Then we introduced molar mass, and that's the mass from the periodic table. We'd been working with those masses in the past. We talked about them in terms of atomic mass units, but then we discovered that an atomic mass unit is equal to a gram per mole. And a gram per mole is the way that we count atoms and molecules, because we don't have the ability to do it in the normal way of counting. 1, 2, 3, 4. We can't do that with atoms and molecules because they're too small and they're in too vast a quantity. So the only way that we can accurately count them is to weigh them. And that's where this mass comes in, this mass that offers a relationship between the quantity and the mass. And that's what the stuff on the periodic table is all about. And so I think then what we did is we also had a little bit of practice of adding up the molar masses of some compounds. And so that's where I want to start there. I just want to start with a couple of practice problems, and let's see if we can get warmed up. So let me turn on take me a second to log in. Still don't know what's going on with this thing, why it's not working. All right, so let's do this. How many water molecules are contained in a 7.9 times 10 to the negative 6 kilogram sample. So I'm not starting out at the easiest possible place. I want to get you warmed up, but we need to remember how to do some of these other conversions. And so I want to walk you through this one to make sure that we're all on the same page. So what are you given? You're given 7.9 times 10 to the negative 6 kilograms of water. What we want to know is the number of water molecules. That's what it asks. How many water molecules? So the basic plan is to convert kilograms of water, a mass, into the number of water molecules. We don't really know how to do that. There's not a direct conversion, so we have to do some step-by-step work. We know that we can convert kilograms to grams of water, and we can use the molar mass on the periodic table of elements to convert grams of water to moles of water. And then once you know moles, as long as you use the relationship between moles and the number, and that number, remember what we called that number? The number's name. The name of the number is Avogadro's number. That's 6.026 times 10, oh, I'm sorry, 6.022 times 10 to the 23rd. That's called Avogadro's number. As long as we know that relationship, then we can do this calculation. What things do you have to know by heart? You have to know this conversion value by heart, and you have to know this conversion value by heart. The conversion value between the mass of water and the number of moles, you're going to get that from the periodic table of elements. So let's try to put all this together. We had 7.9 times 10 to the negative 6 kilograms of water. 1 kilogram is 10 to the minus 3 grams. Then we know that 18.02 grams of water is 1 mole of water. Now, how did I get this? I went to the periodic table of elements, and I saw that hydrogen is 1.08 grams per mole. I saw that oxygen is 16.00 grams per mole. And I have 2 hydrogens and only 1 oxygen. So when I add them all up, I get 18.02 grams per mole. 16 plus 1.008 plus 1.008 is 18.00 or 0.16, and then rounded up to 2 sig figs, it's 18.02. Now here's where Avogadro's number comes in. I know that 1 mole of water is 6.022 times 10 to the 23rd water molecules. And there we are. That's the whole setup. And so the rest, of course, is not chemistry department. The rest is the math department. And so we'll let the math department sort of do their work now. 7.9 times 10 to the negative 6 times 10 to the negative 3 divided by 18.02 times 6.022 to the 23rd power. You get 1, 2, 3, that's 9, 12, 13, 14. And I had to count, make sure 3, 6, 9, 12. I got that. Does anybody agree or disagree? I just want to make sure because I have to count. My calculator is really not helpful. Anybody else get that? Cool. Cool. All right, so let's do one more problem before we introduce new material. I want to make sure that everybody's on the same page. There's no rush. We need a lot of practice with this kind of stuff. It is some of the more challenging problems that we can get to in this course. Not quite as the most challenging, but we're getting there. Let's think. If it is found that a sample of, let's come up with something. How about xenon tetrafluoride? There's a good one. Has 9.16 times 10 to the 24 fluorine atoms. What mass in grams of xenon tetrafluoride is the sample? Okay, so we're starting to get a little bit more challenging, and I don't think we did one this direction. So this brings in something else that we brought up last Wednesday, which was the idea that we can use the formula of a molecule as a conversion factor. And what I'm saying to you is that I have a particular number of atoms, but the molecule is xenon tetrafluoride. And so we know that there's a constant composition of xenon tetrafluoride, and that for every one molecule of xenon tetrafluoride, there are 4 atoms. There are 4 atoms of fluorine. And so the question is asking us, if for some reason, I'm not telling you how I did this, but if for some way I'm able to figure out how many fluorine atoms there are in a sample of xenon tetrafluoride, then I could figure out what the mass of the sample of the molecule is. And so what am I given? I'm given that that we know there's 9.16 times 10 to the 24 atoms of fluorine. I'm asked for the mass, and I'm going to erase mass and just use grams. I'm asked for the mass in grams of xenon tetrafluoride. So that means that I need to go from the number of fluorine atoms to the mass of xenon tetrafluoride. And so we got to figure out how to do that in a step-by-step fashion. And so I think at this point, I might want to do something like work from both directions at the same time and see if you can see how this plan comes together. Well, I know that I can go from number of fluorine atoms to moles of fluorine atoms. And once I have moles of fluorine atoms, I can go to moles of xenon tetrafluoride. And once I have moles of xenon tetrafluoride, I know how many grams I have. But this is one of those examples when there's more than one path. I showed you a problem last time where there was more than one path, and there's more than one path here as well. So I can go from number of fluorine atoms to the number of xenon tetrafluoride molecules. And from there, I can go to mole of xenon tetrafluoride. And from there, I can get grams. So what I want to point out, and I've sort of hidden it, and so let me just kind of unhide it so that it's a little bit more clear. Number of fluorine to mole of fluorine. There's more than one path, and that doesn't mean that one path is better than the other. It just means that there's more than one way to solve the problem and get the same answer. Last time I illustrated that you're going to do all of the same mathematical calculations. You're just going to do them in a different order, and the units are going to be in different orders as well. But at the end of the day, you're going to get the same answer. So last time I showed you that you're going to get the same answer because we did both solutions just to prove that we're going to be able to get both the same answer. Well, in this case, what I want to do is I'm just going to work on one, and I'll do the one at the bottom since it's a little bit larger text. So we'll start off with the number of fluorine atoms, 9.16 times 10 to the 24 fluorine atoms. That's the number of fluorine atoms. So how do I figure out the number of xenon tetrafluoride? Well, the number of xenon tetrafluoride is based on this relationship. For every 4 fluorine atoms, there is 1 xenon tetrafluoride molecule. For every 6.022 times 10 to the 23rd xenon tetrafluoride molecules, there is 1 mole of xenon tetrafluoride. And now the thing we have to do is we have to go to the periodic table and we have to add up the molar mass of xenon tetrafluoride. (207.28 grams of xenon tetrafluoride. So we're done with the chemistry. And now all I have to do is get the math out. And so 9.16 times 10 to the 24 divided by 4 divided by Avogadro's number times 206, is it 206? 207 divided by 207.28 multiplied, times 207.28. So let's follow the units just to summarize. Number of fluorine atoms cancel with number of fluorine atoms, converting to the number of xenon tetrafluoride molecules. The number of xenon tetrafluoride molecules cancels. The number of moles of xenon tetrafluoride cancels, leaving us with grams of xenon tetrafluoride. And so I get 788 grams of xenon tetrafluoride. Anybody else get that? $763. Let me just make sure that I... Did you get 207.28? Yeah. The one thing that's good about, even though my calculator is bad and it makes me count, it does keep all of my typing. And I definitely didn't mess up the typing. 207.29. Maybe that's the difference. Doesn't seem like it would be. Let me try to do let me try to use your number and see what I get. Four divided by... I still get 788. So I get 788.27. And so I think 788 is the way to go. So double check your calculation. Do it again. I did it again. You do it again. Avogadro's number. My bad. Okay, cool. Yeah, it's easy to make little mistakes. You guys see the mistakes that I make all the time. And Adi pointed out that in the nomenclature video for polyatomic ions, and I'll go ahead and say this, I went through all of the the halogen-based oxo anions. There's the 16. And I did chlorate, bromate, iodate, chlorite, bromite, iodite, and then I went pair chlorate, pair bromate, pair iodate, and then I went hypochlorite, hypobromite, and then I said hypoiodate. And I actually wrote it down, hypoiodate. And we just went on. There isn't a hypoiodate. I totally made a mistake. Now I did correct it in the description of the video, and eventually I'll have to edit that video to fix the mistake. But I want to point out that I do make mistakes. And so if you think that there's something that's wrong, you should definitely say something so that we can address it. Most of the time, I think we're catching them as we go, but sometimes some might slip through. And so if it's easy for me to make mistakes, think about how easy it is for you to make mistakes. And so double check, if you've got time, run the calculation through your calculator twice so you know you've got the right answer, or at least you're as certain as you can possibly be. Just some general advice. Okay, any questions about that? Any questions? (207.28) was the molar mass of xenon tetrafluoride. Well, I already erased it, Shaq, so I'm not going to show you the other way, but it is essentially the exact same path. So what I would encourage you to do, it's not the exact same path, but it's the exact same calculation as far as numerical considerations are concerned. Rewind the video back to that point. Go back and review it and do that other pathway on your own and compare it to the one that we did and see for yourself, convince yourself that, yeah, all we're really doing is we're changing the relationship slightly, but the mathematics is the same. We're going to get the same answer. And we should, right? Because this is all based on physical reality. And if we're asked a question about physical reality, no matter which way we approach the question, we should always get the same answer. Okay. And so what we're doing is we're starting to get a lot real close to the end of this 6th unit. And what I want to do now is bring up this next piece. And this next piece is pretty important because of the following reason. It goes like this. We've been doing a lot of work doing problem solving in a particular way with a particular strategy. The next bit of information will involve some problem solving that the strategy that we've been using won't be particularly helpful for. In fact, I feel like it adds an extra degree of confusion, and so we won't use that method. So we are going to take a break from that method to do this one particular set of problem types. But I think it will remind you about figuring out the molar mass of a compound from the percent abundances. It'll be like that in a sense. And so let's go into it. So we have to talk about mass percent composition. We have to talk about empirical formula. And we have to talk about molecular formula. And we have to talk about the problems that are presented to us that help us determine empirical formulas from mass percent compositions or from mass breakdowns of compounds. And that problem solving method will be different than the one that we've used before. So get your brains flexible. It is a little bit serious time, but what I'm asking you to do is just be flexible. It's challenging already because you're learning a bunch of new material, but you got to be able to learn it in different ways. And I do my best to approach the problem solving the same way every time, but I think you'll see that this particular type of problem doesn't lend itself into that same conceptual organization that we've been doing. And so we'll just have to do something different. And so let's kind of jump into that. Let's see what we mean by mass percent composition and empirical formulas. Let's start off with mass percent composition. I think you'll find this to be pretty straightforward. The mass percent composition of a compound is the percentage of the mass of the compound due to the mass of one element in the compound. So there's a formula for that, actually, and it's this. The mass percentage of X equals the total mass of X divided by the mass of the compound times 100. So it's another percentage, right? And I think at this point, you should be familiar with percentages. Percentages are parts divided by wholes times 100. If we're talking about the mass percent, well, what's the part? It's the part of the mass due to whatever component we're talking about. And in this case, we talk about components in terms of elements. Okay, so the part is the mass of the element in the compound. Well, what's the whole? The whole is the entire mass of the compound. And then we multiply it by 100. So let me give you an example. What is the mass percent composition of both oxygen and hydrogen in water? Okay. What's the mass percent composition of oxygen and water in hydrogen? Excuse me. I said that all backwards. What is the mass percent composition of oxygen and hydrogen in water? So remember that if I give you a compound, there will be a mass percent composition for every element in the compound. In water, it's easy because there's only 2 elements. So we know that already. We know there's only 2. But in compounds that have 5 or 6 different elements, then there will be 5 or 6 different mass percent compositions, one for each element. Now, what should we know about all of the mass percent compositions? If we add them all up, what should we get? Right. If you take all of the hundreds, all of the mass percent compositions, and you add them up, you'll get 100. Someone says, is the mass percent composition 33.3% oxygen and 6.6% hydrogen? That isn't the mass percent composition. That is the percentage of the number of atoms in the compound. There are 2 atoms of hydrogen in the compound, and there are 3 total atoms in the compound overall. So the percentage of the number of atoms for hydrogen is 66%. There is 33% of the atoms are oxygen, but we're talking about mass. So we have to add up the mass. And let's do that. What is that molar mass of water? Remember, it was 2 times 1.008 grams per mole for hydrogen. We got 2.016 for that. And so let's make this be just hydrogens. So 2 times hydrogens, and 1 times oxygen was 1 times 16.00 grams per mole. that got us 16.00 grams per mole. So here is the total mass of hydrogen, and here is the total mass of oxygen. So I actually do know the numerators now. 16.00 grams per mole for oxygen and 2.016 grams per mole for hydrogen. Now I need to know the total mass, right? And I think everybody's starting to do that now. The total mass of water is 18.02 grams per mole. 18.02 grams per mole. And so I put that down in the denominator. Now, this was a common mistake that I saw in my lab class, and a lot of you are in that class, so I just want to go ahead and briefly talk about it. When you divide two numbers, you have to divide the units. And if the units are identical, they cancel out. And so you do need to deal with that, right? There's not going to be any units in the percentage. There should never be a unit in the percentage. Look at the 2 grams per moles canceling out. Okay, the rest is just some calculator work then. What do you get? 16 divided by 18.02 times 100. This one is 88.79%. What about hydrogen? We could calculate it, right? We could just subtract 88.79 from 100, and we should get 11.21. Well, let's see if we actually do. Let's see. We'll take 2.016 and divide it by 18.02. And what do we get? 11.19. Did I do this wrong? Now what happens when I add 11.19 plus 88.79? What do I get? I get 99.98%. What's the problem there? What's going on there? What's the problem there? Why isn't it adding up to 100? Yeah, it really is. This is a good example of just some rounding errors, right? If we let the calculators keep all the decimals that it gives us and we don't think about sig figs or do any rounding in the interim, then we'll get a number that's essentially right on the number on the nose to 100. But we did some rounding in the interim. For hydrogen, I've got 2.016. I've got 3 decimal places, but for water, I've only got 2 decimal places. If I were to keep it, I could have said 18.016. That'd have been a little bit of a different number, and I would have got a little bit of a different answer. Let's try that. 2.016 divided by 18.016. I still get 11.19, so that's not quite different. But it's, at the end of the day, it's just a rounding number. It's just a rounding error. And so this is where your number sense is going to come in. Your number sense has to come into play here. Is 99.98, is that 100%? Let me ask this question in another way. Yeah, so let's do 18 divided. This is a good suggestion. Angela has a good suggestion. 16 divided by 18. 16.00 divided by 18.016. That gets us 88.81. That sure does, doesn't it? If we use all the decimals over here, it's where it changes. 88.81. Now that's 100, right? Yeah. And so the other thing I was talking about was 99.98. Is that 100? Is that 100%? This is your number sense. Yes, the answer is yes, right? The only thing that we're having some issues with there are rounding errors. You are seeing firsthand what rounding errors can do and how they contribute to the overall area of error in a calculation. It doesn't mean we're wrong. It just means that there's some errors in rounding, and that they propagate and they lead to overall numbers that don't add up exactly what you would think. We get 99.98 instead of 100. But that means we're still okay, because 99.98 is essentially 100. Would you be worried if you got, that is an example of precision, exactly. You see how our precision is limited by our rounding and the number of significant figures that we use. Would you be worried if you got 100.02? If you added up and you got 100.02? Would you be worried about that? Why? Why would you be worried about that? 99.98 is 0.0. No, it's still a rounding error. It's still just a rounding error. It's still just a rounding error. It can't be more than 100% based on physical reality, but can it be more than 100% if we have some rounding errors? I'm getting a lot of good discussion, I think, in this chat. It seems like everybody's okay. Nobody has any sort of conceptual problem with 99.98%. But when I suggested this, you guys panicked. There was panic in the streets. We're going to get to some of those other suggestions in just a second, Adi. How far off from 100 is this one? It's 0.02% off. How far off is this from 100? 0.02%. It's the same error, just in a different direction. So there really is no difference between these two values when we're thinking about it in terms of error, right? In terms of error, they're both essentially the same. Now, when should we worry? When should we get some worrying going on? I saw a couple of examples. If it adds up to 110%, should you worry? Should you go back and redo your work? Definitely. Yeah, that's way over. What if you get, yeah, that's a big difference. What if you get 101%? Oh, whoa, 101%. Yeah, even just a single percentage point, that's too far off. Yeah, we need to go back and recheck. A couple of 100ths in a decimal place, we're okay. But a whole percentage point? No, we got to go back and check that. That's more than a rounding error. Okay, so let's do another practice problem. Let's continue to calculate the mass percent composition of a compound. Let's make it a little bit more. Yeah, so 98.2%, that's not going to work out. That's 1.8% off from where I need it to be. So that's not good, no. So let's calculate the mass percent composition of all elements in glucose, which is C6H12O6. Right, so let's do this practice problem. Let's calculate the mass percent composition of all elements in glucose, C6H12O6. So that means I'm going to have a mass percent composition for carbon. I'm going to have a mass percent composition for hydrogen. And I'm going to have a mass percent composition for oxygen? So what I want you guys to do right now is I want you to add up the molar mass of glucose. I'm going to just rewrite this to get some more room. So go ahead and take some time right now and add up the molar mass of glucose. Take those 12 hydrogens, the 6 carbons, and the 6 oxygens, and add them all up, and let's see what we get. What do we get? Well, there are 6 carbons, and the molar mass of carbon is 12.01 grams per mole from our periodic table. So what do we get for that? 12.01 times 6. That's 72.06 grams per mole. What do we get for hydrogen? There's 12 times 1.008 grams per mole. What do we get there? Well, 12.096 grams per mole. And then for oxygen, there's 6. Oxygen's a little heavier, 16.00 grams per mole. So that's 96.00 grams per mole. Yep, I think that's about right. 180 is the number that comes to my brain. So we get 96.00 plus 12.096 plus 72.06. I get 180.156. 180.156. But I'm going to round that to two decimals, since the numbers that I'm adding together, the least of them have 2 decimals. So I'm going to go ahead and round that at this point. The total mass is 180.16 grams per mole. And now that I've figured that out, that's going to be the denominator in each one of these calculations. And I've also figured out the numerator in each one, 72.06 grams per mole, 12.096 grams per mole, and 96.00 grams per mole. So a little bit more dividing and some multiplying by 100. So 72.06 divided by 180.16. I get 39.997%. So that's actually, even with 2 decimal places, that's 40.00%. 12.096 plus 180 are divided by 180. 0.16, I get 6.714%. And then finally for oxygen, 96 divided by 180.16, I get 53.29%. Let's add them up. Let's check our work. 53.29 plus 40 plus 6.714. We get the total, just to check, let's check our total just to check our work. We get 100.004. Seem like we probably did it okay? Or is this okay or not? Is this okay? Question mark? Yeah, right. That's fine, right? That's totally fine. And in fact, if I were to change this to 2 decimal places, round it to 2 decimal places, just so that I have the same number of decimal places, I'd get exactly 100 in this case for my total check, my check total. So remember, we can check our work by adding them all up to see if we get 100. So that way we know if we got it right? Because if it doesn't add up to 100, then it's not right. If it does, then it is right. So now we've done it. We've done the mass percent composition based on the formula. There's another way to do mass percent composition. There's another way to do it. What if I said this? What if I said something like this? Stand by, I'm looking for an example because I can't just make this example up. Yeah, recheck that, Adi. That's definitely, did you get 53.29, 6.71, and 40%? Okay, so let's try this. A 200 gram sample containing carbon, hydrogen, and oxygen is found to have 124.08 grams of carbon, 20.082 grams of hydrogen, and I could just make this one up, 55.10 grams of oxygen. What is the mass percent what's the mass percent composition of all elements? Is it 200 grams? Well, the formula didn't change, right? The mass percent composition is still the total mass of the compound divided by the mass of the element times 100. It's different though, right? Instead of giving you a formula, now I'm giving you an actual experimental breakdown of the different components. There's still 3 components, so there'll be 3 different mass percent compositions. They'll all add up to 100 still. The only question is okay, I didn't give you a formula, so you can't just use the periodic table to come up with it. But can you figure out the mass of carbon divided by the total mass? It's not working backwards. No, it's just giving you the data in a different form. It's giving you the data it's the same as what you just did. It's the same as what you just did, except you're not using the periodic table to get these 2 values. In order to get these 2 values, you're just looking at the data. Okay, well, what's the total mass of the compound? Read the word problem. What's the total? Right. The total mass of the compound is 200 grams. You have a 200-gram sample. So the total mass of the compound is 200 grams. Well, what's the mass of the element? Carbon in this case. Yeah, it's given to you. 124.08 grams. So in this case, it's actually easier because you're just looking at the numbers that you're given and you're just putting them in the calculation. So 124.08, what do you get? 62.04%. What's the percent hydrogen? And what's the percent oxygen? So same thing, just use the same values. We know that the entire compound is 200 grams. It tells us what each of those elements, what their masses are. 55.10 grams for oxygen and 20.82 grams for hydrogen. So we should get 10.41% here, and we should get 27.55% here. Yeah. Any questions about this one? Questions about this one? Okay, if there's no questions, let's do one little thing. Let's just define empirical formula, and then we'll be done for the day at that point. So that's mass percent composition. But maybe now what I want to do is define molecular formula as well. Do we have to remember this formula? Yeah, you do. Look, you do have to know it. And the reason is this. Percentages are something that you should know how to calculate. If I tell you to calculate the percentage of anything, you should be able to do it. It's part divided by whole. What kind of percentage it is determines what the part and the whole is. If it's the mass percent composition of a compound, then what's the whole? Well, it's the whole mass of the compound. What's the part? It's the part of that compound, the element, and its mass. So the part would be the mass of the element. The whole is the mass of the compound divided times 100. So you do have to know that. So we are either, your question's just a little confusing. I'm not sure what you're asking me. Yes. So you're either going to be given the formula or you're going to be given the actual masses of the compounds. Right. Yeah. So you'll either be given the formula, in which case you have to calculate the masses of each component and the total mass of the compound, or I'll just give you an actual set of data from some experiment and say, hey, we had a sample. Here's what the sample weighed. We determined the mass of each of the atoms were X, Y, and Z. So, but the formula is the same each case. Okay, so let's take this time to specifically define molecular formula before we talk about empirical formula. We've been using molecular formula. I think you'll see that it's just the list of the types of elements and their numbers in a compound. It's the list of elements and their numbers in a compound. I think, does that fit the definition we've been using so far? We didn't specifically define it before, but that's the number, that's what we've been using. Empirical formula is just a little bit different. It's the lowest whole number ratio of elements in a compound. Grammar police got me. Told me I was going to go to grammar jail if I didn't change that. That was not a thank you. That was not a thank you. Good times, good times. Okay, so what's the difference here? With a molecular formula, I'm telling you what are each element and how many of those elements there are in the compound. The empirical formula is similar in the fact that I'm going to tell you what elements are in the compound, but it's the lowest whole number ratio of elements. It's not the actual number that there are. So that means there's going to be times when the empirical formula and the molecular formula are the same, but there's going to be times when it's not. Here's an example of when it's the same. So let's switch colors actually so that we have some designation. Here's the molecular formula. Here's the empirical formula. Oh, wait. Nah, I spelled it right. Yeah, my grammar is much better in languages that I don't speak firsthand because I didn't use any of the shortcuts. So now I know them all. Okay, so I digress. I was just messing with one of the students there. Diana just needed to get messed with a little bit since she's my grammar police. Molecular formula. Let me give you an example. H2O. What is the lowest whole number ratio of elements so that I can determine the empirical formula? Well, don't forget, what is the number that's here that's not stated? We don't write it down, right? It's 2, exactly. It's 2 to 1. Is that the lowest whole number ratio already? Yes, right. You can't lower any of those values any further to get whole numbers. So the empirical formula of water is also H2O. But maybe you like to bleach your hair and you use hydrogen peroxide to do that. The ratio here is 2 to 2. How can you change that to be the lowest whole number ratio? What would be the empirical formula in this case? Just HO, right, 1 to 1. So this is the difference between empirical formulas and molecular formulas. Let's do a couple of other examples real quick. How about, we did this one earlier, C6H12O6, glucose. What's the empirical formula of glucose? What's this empirical formula of glucose? If I divide every number by 2, I get 3 to 4 to 3, right? Is that right? No, I did that wrong. Not 4. I get 3 to 6 to 3. So if I divide every number by 2, I get 3 to 6 to 3. Is that the lowest whole number ratio? I think some of you guys are telling me already the answer to that. Is that the lowest whole number ratio? No, it's not, is it? In fact, I can divide this again by 3 to get 1 to 2 to 1. So the lowest whole number ratio of atoms is 1 to 2 to 1. CH2O. It's the empirical formula. Yeah, divided by 6 in this case. Well, there is a molecule called formaldehyde. And the formula for formaldehyde is C2, or excuse me, is CH2O. The empirical formula for formaldehyde is also CH2O. So I want to make sure that I'm illustrating the limits. I want to make sure that I'm illustrating the limits. The empirical formula prevents us from distinguishing one molecule from another molecule. Sometimes, right? We can certainly distinguish some things, but here's an example that we couldn't, right? We couldn't tell by empirical formula whether or not we're talking about glucose or formaldehyde. We can't tell. We need the molecular formula for this. And so let me finish off, and I'm going to leave it here today at empirical formula. Why do we use empirical formula? Well, there's 2 reasons. One, we're going to do a bunch of problems that involve the empirical formula and calculations. So briefly, I can give you the mass percent composition and you can calculate an empirical formula. Again, if I give you the mass percent composition, you can calculate an empirical formula. So that's one reason, right? We're going to do some problems with it. What's the other reason? Well, there's a type of spectroscopy called atomic absorption spectroscopy. And what it does is it takes an element or a compound and it throws it into a machine and it breaks it up into its elements. And you really can get an idea what the empirical formula is from this type of spectroscopy. So the reason why we talk about empirical formulas is that it really is directly related to a type of experiment that you can do in real life with different compounds. And so I'm going to leave it there for the day, and we'll come back and we'll start with empirical formulas, and we'll use we'll use mass percent compositions to calculate empirical formulas.